The development of brain-computer interfaces capable of restoring speech through direct neural decoding represents one of the most exciting frontiers in neuroscience and biomedical engineering. This technology brings together the fields of neurophysiology, materials science, machine learning, and speech synthesis. In this article, I will describe in detail the microelectrode arrays that capture neural signals, the neural patterns involved in speech production, the computing systems that decode these signals into speech in real time, and the specific devices and products that enable these breakthroughs. Microelectrode arrays are highly specialized tools that serve as the interface between living brain tissue and electronic equipment. They are composed of grids or clusters of extremely small electrodes, often made from biocompatible materials such as silicon, platinum, or iridium. These electrodes are designed to either penetrate the brain or sit on its surface, depending on the goals of the study or therapy. The size of each electrode is typically measured in micrometers, allowing the array to detect the electrical activity of individual neurons or small groups of neurons. The electrodes can record the electrical impulses known as action potentials, as well as broader local field potentials which reflect the activity of neuron populations. The signals gathered are extremely small in amplitude and require amplification and filtering before they can be processed. Some arrays are designed for recording only, while others can both record and stimulate neural tissue. The choice of array depends on the application, the target region of the brain, and the intended duration of implantation. Speech production involves the coordinated activity of several brain regions, each contributing distinct functions. The inferior frontal gyrus, known commonly as Broca's area, plays a critical role in planning the movements needed for speech. It generates the sequence of motor commands required to produce particular sounds. The primary motor cortex executes these commands by sending signals to muscles involved in speech, including those controlling the lips, tongue, larynx, and diaphragm. The supplementary motor area and premotor cortex contribute to initiating speech and preparing the movement patterns. The auditory cortex provides feedback by processing the sound of the speaker's own voice, allowing real-time adjustments. The posterior superior temporal gyrus, often called Wernicke's area, is involved in the comprehension of language and links meaning to speech production. The neural signals involved in speech are time-locked and highly organized. They consist of action potentials that encode precise timing information needed to control speech muscles and local field potentials that reflect the synchronized activity of neural circuits. These signals are mapped somatotopically in the motor cortex, meaning specific regions of the cortex correspond to control of specific muscles or muscle groups. Brain-computer interface systems designed to restore speech must capture these signals and translate them into audio output with very low delay. This requires sophisticated computing hardware capable of real-time processing. The neural signals are first acquired using systems like the Blackrock Neuroport or Blackrock Cerebus. These platforms support recording from arrays such as the Utah array, which features 96 or more electrodes capable of sampling at rates up to 30,000 Hz per channel. Ripple Grapevine is another platform used for neural signal acquisition, providing similar capabilities. The raw neural data is passed to processing hardware which may include digital signal processors, field programmable gate arrays, or graphics processing units. These components handle the initial filtering, amplification, and feature extraction steps. Field programmable gate arrays such as the Xilinx Kintex or Altera Stratix series are often chosen for their ability to process large volumes of data in parallel with minimal delay. Once the features are extracted, the neural decoder takes over. This is typically implemented on powerful computing hardware such as servers equipped with Intel Xeon processors or on embedded platforms like the NVIDIA Jetson Xavier or Jetson Orin. These platforms run machine learning models that map the neural features to phonemes, syllables, or full words. The models may include recurrent neural networks, long short-term memory networks, or transformer-based architectures. The decoders are trained on data collected from the individual user, allowing the system to learn that person's unique neural patterns. After decoding, the output is passed to a speech synthesizer that generates audio. The synthesizer may use traditional parametric techniques such as formant synthesis or modern neural network-based models like fast speech or WaveGlow. The entire processing chain, from neural signal acquisition to audio output, is designed to operate with latency below 25 milliseconds. This is critical because human speakers expect to hear their own voice almost instantly when they speak. Any delay greater than this can disrupt the natural flow of conversation. Specific systems that have demonstrated this capability include the speech neuroprosthesis developed at the University of California, San Francisco. This system combines Blackrock Neuroport recording hardware, field programmable gate array preprocessing, Intel Xeon server class decoding computers, and real-time neural speech synthesis. The Stanford University BrainGate collaborators have used similar setups, pairing Blackrock hardware with custom field programmable gate array preprocessing and custom neural decoders. Paradromics is developing a platform called Argo which aims to provide massively parallel neural recording combined with low latency decoding. Though still in development, Argo represents the next generation of high channel count brain-computer interfaces. The neural decoders employed in these systems are highly specialized. They must interpret patterns of spikes and local field potentials across dozens or hundreds of channels, converting them into linguistic units in real time. The models are often pruned or simplified versions of larger deep learning architectures, optimized to run at high speed on dedicated hardware. They continuously update predictions as new neural data streams in, ensuring the output is fluid and responsive. The speech synthesizers that follow are designed to produce intelligible, natural-sounding speech with correct pitch, tone, and rhythm. Systems such as WaveGlow or real-time variants of Tacotron have been adapted for this purpose, often running on graphics processing units to meet the demanding performance requirements. The success of these systems represents a major milestone in the development of assistive technologies for people who have lost the ability to speak. Unlike earlier interfaces that allowed users to select letters one by one, these speech neuroprosthetics can restore natural conversational speed and expressiveness. They capture not just the content of what the person wants to say but also the emotional tone and prosody that are so important for effective communication. The systems also highlight the importance of cross-disciplinary collaboration. Advances in electrode design, signal processing algorithms, machine learning models, and speech synthesis have all contributed to these breakthroughs. Each component must function at the highest level of performance to enable real-time speech restoration. Looking ahead, researchers aim to refine these technologies further. One goal is to improve the accuracy and vocabulary size of the decoders so that users can produce more complex and varied speech. Another priority is to make the hardware smaller, more power efficient, and less invasive. Flexible electrode arrays that conform more closely to the brain's surface are under development to reduce tissue damage and inflammatory responses. Wireless systems that eliminate the need for tethered connections are also being pursued, as they would reduce infection risk and improve user comfort. Ethical and regulatory considerations are becoming increasingly important as these systems move closer to clinical deployment. Issues of privacy, data security, and equitable access must be addressed to ensure that the technology benefits all who need it. The integration of microelectrode arrays, neural signal decoding, and high-performance computing has enabled the creation of brain-computer interfaces that can restore speech in real time. The specific devices involved include the Blackrock Neuroport and Cerebus systems, Ripple Grapevine interfaces, field programmable gate arrays like Xilinx Kintex and Altera Stratix, NVIDIA Jetson embedded processors, Intel Xeon servers, and speech synthesis software such as WaveGlow and FastSpeech. These components work together to capture, interpret, and vocalize the neural signals associated with speech, providing a powerful tool for individuals with severe speech impairments. Continued research and development promise to make these systems even more capable, accessible, and transformative in the years to come.